Hello and welcome to the Domain on Security Architecture and Design of the CISSP certification course offered by Simplilearn. Security Architecture and Design is one of the 10 domains of Common Body of Knowledge, or CBK, for the CISSP certification exam. The first part of this domain covers the logical models required to keep the system secure. The second part covers evaluation models, which quantifies how secure the actual system is. And the third part covers the hardware and the software required to achieve a secure computer system. The objectives of this domain will be discussed in the following screen. After completing this domain, you will be able to describe the architecture frameworks, describe the security models, list the types of evaluation criteria, describe the enterprise and system security architecture, list the types of distributed systems, recognize security threats, and identify countermeasures. In the first topic, we will look at architecture frameworks. Kevin Butler is a security administrator in the Network Firewalls Division at Nutri Worldwide, Inc. He is preparing for his CISSP exam. As a part of his preparation, Kevin read the internal case study on security architecture and design. The case study talks about the following. In the last financial year, Nutri Worldwide Inc. expected a large increase in IT infrastructure requirements. The management felt the need to implement best practices for IT service management. Hilda Jacob, General Manager of IT Security, was assigned a task for selecting best framework to help the organization identify, plan, deliver, and support IT services to the business. It is important to know the different security architecture and designs to identify the right framework for such requirements. Hilda had decided that the framework would be ITIL. Kevin understands that he needs to learn the different security architecture and designs to be well prepared for his examination. Let us start with our first topic, architecture framework, which deals with the creation and maintenance of a good security architecture. In this topic, we will define architecture frameworks and list their uses. We will also discuss the common architecture frameworks. In this screen, we will look at the definition of architecture framework in detail. ISO 42010 defines architecture framework as an architecture framework establishes a common practice for creating, interpreting, analyzing, and using architecture descriptions within a particular domain of application or stakeholder community. The role of the security architect is to translate business requirements into security solutions for key assets. Designs are created using standardized methodologies to maintain consistency between different architects. To ease the acceptance of their designs, security architects can take advantage of common architecture frameworks used across multiple industries and disciplines. An architecture framework provides a structure used for developing a broad range of security designs. The common features of an architecture framework are: it describes a method for designing a target state as an integrated set of systems or system components. It provides a set of tools to ease architecture development. It provides a common vocabulary. It also frequently includes a set of recommended standards and operational practices. It may also include information on compliant vendor products, modules, or components that can be used as design elements within the framework. In the subsequent screen, we will talk about the common architecture frameworks. In this screen, we will discuss the ISO IEC 27001 and 2005 security standards. An Information Security Management System, ISMS, is defined as the governance structure supporting an information security program. ISO IEC 27001-2005 is focused on the standardization and certification of an organization's ISMS. ISO IEC 27001-2005 provides instructions on how to apply the ISMS concept and to construct, run, sustain, and advance information security management. The ISO IEC 27001-2005 standard is focused on 5 key areas. They are: general requirements of the ISMS, management responsibility, internal ISMS audits, management review of the ISMS, ISMS improvement. In the next screen, we will discuss ISO and IEC 27002 Code of Practice for Information Security Management. ISO IEC 27002 provides a Code of Practice for Information Security Management, which lists security control objectives and recommends a range of specific security controls according to the industry best practice. ISO IEC 27002 includes the following 11 focus areas. Security policy provides management guidance and support for information security. Organization and information security provides a formal and defined security mechanism within an organization that includes information processing facilities and information assets assessed or maintained by third parties. Asset management protects the organization's assets by ensuring valuable data assets are identified and receive appropriate protection. Human resources security minimizes the risks of human error, theft, and misuse of resources. It provides information security threats and concerns to users and disseminates information to support the corporate security policy. Physical and environmental security prevents unauthorized physical access, damage, and interference to facilities and data. Communications and operations management ensures the proper and secure operation of data processing facilities by protecting software, communications, data, and the supporting infrastructure, as well as ensuring proper data exchange between organizations. Access control limits access to data, mobile communications, telecommunications, and network services, as well as detects unauthorized activities. Information systems acquisitions, development, and maintenance implement security controls into operations and development systems to ensure the security of application systems, software, and data. Information security incident management implements procedures to detect and respond to information security incidents. Business continuity management mitigates an incident's impact on critical business systems. Compliance ensures adherence to criminal and civil laws and statutory, regulatory, or contractual obligations. It also complies with organizational security policies and standards and provides a comprehensive audit process. The next topic is security models. Security models are the rules to be implemented to support and enforce security policy. In this topic, we will define security models, discuss common security models, and look at a few examples of security models. A security model is a specification that describes the rules to be implemented to support and enforce the security policy. A formal security model describes and verifies the ability to enforce security policy in mathematical terms formally. Given the demands of formal verification, most models are focused on system-level security architecture at the component level. In most cases, it would be too difficult or time-consuming to formally verify all aspects of large-scale security architectures. A CISSP candidate is expected to understand the general types of security models as well as some specific examples. It is essential to remember the ultimate goal addressed by the model and how each new model builds on the information provided by earlier models. In the next screen, we will look at the common security models. In the next few screens, we will discuss examples of security models. Let us start with Bell-LaPadula Confidentiality Model. Bell-LaPadula Confidentiality Model is focused on maintaining the confidentiality of objects. Its primary goal is to prevent disclosure as the model system moves from one state, one point of time, to another. Bell-LaPadula includes the following rules and properties. The simple security rule states that a subject cannot read data at a higher security level than they are cleared for. A subject can read all documents at or below the level of specified security. However, the subject cannot read any documents above the specified level of security. This is called no read up or NRU. The rule prevents subjects from learning secrets at a higher level than their own. For example, a diplomat can read documents intended for common citizens, however, cannot read documents intended for the president. The star property rule states that a subject cannot write data to an object at a lower security level. The subjects can write, create, or modify documents at or above their level of security, however, cannot write documents below their level. This is called no write down or NWD. This rule prevents subjects from accidentally leaking secrets at their level into a document at a lower level. For example, a diplomat can write documents intended for the president, however, cannot write documents for common citizens out of concern that the diplomat may accidentally leak sensitive information to the common citizens. The strong star property rule states that a subject can perform read and write functions only to the objects at its same security level. Some of the limitations of this model are the following. It only considers confidentiality and does not mention other properties, such as integrity and availability, or more sophisticated modes of access. It does not address important confidentiality goals, such as need to know, and the ability to restrict access to individual objects based on a subject's need to access them. It does not provide a mechanism for a one-to-one mapping of individual subjects and objects. We will talk about another example, Biba Integrity Model, in this screen. Biba Integrity Model protects the integrity of the information within a system and the activities that take place. It addresses the first goal of integrity. Biba is often considered as the first formal integrity model as it prevents modifications of data by unauthorized persons. It is also known as Data Integrity Model. Biba addresses the shortcoming in the Bell-LaPadula model where a subject at a lower security level is able to overwrite and potentially destroy secret information at a higher level. Using the invocation property, Biba also addresses the problem of one subject getting a more privileged subject to work on their behalf. The following are the axioms of Biba Integrity Model. The simple integrity axiom states that a subject cannot read data at a lower integrity level. The subjects cannot read documents below their level. This is called no read down or NRD. For example, a diplomat can read documents written by the president but cannot read documents written by common citizens. The star integrity axiom states that a subject cannot modify an object at a higher integrity level. This is called no write-up or NWU. For example, a diplomat can write procedures to be read by common citizens, but cannot write procedures to be read by the president. In this screen, we will discuss another example of security models, Clark-Wilson Integrity Model. The Clark-Wilson model addresses the shortcomings in the Biba model by focusing on integrity at the transaction level and addressing three major goals of integrity in a commercial environment. The Clark-Wilson Integrity Model provides a foundation for specifying and analyzing an integrity policy for a computing system. The model is primarily concerned with formalizing the notion of information integrity. Information integrity is maintained by preventing corruption of data items in a system due to either error or malicious intent. An integrity policy describes how the data items in the system should be kept valid from one state of the system to the next and specifies the capabilities of various principles in the system. The model defines enforcement rules and certification rules. It addresses three goals of integrity, which are: subjects can access objects only through authorized programs or access triple, separation of duties enforced, and auditing is required. We will talk about the last examples of security models, Breuer Nash, Graham-Denning, and Harrison-Russo-Ullman models in the next screen. Following are other important security models. The Breuer and Nash model was constructed to provide information security access controls that can change dynamically. This security model is also known as the Chinese wall model. It was designed to provide controls that mitigate conflict of interest in commercial organizations. The Breuer and Nash model is built upon an information flow model. In this model, no information can flow between the subjects and objects in a way that would create a conflict of interest. The Graham-Denning model is a computer security model that shows how subjects and objects should be securely created, deleted, assigned rights or privileges, and how ownership of objects is managed. It also addresses how to assign specific access rights. This model is mainly used in access control mechanisms for distributed systems. The Harrison-Russo-Ullman model is similar to the Graham-Denning model. This model is composed of a set of generic rights and a finite set of commands. It is also concerned with situations where a subject should be prevented from ever gaining particular privileges. To do so, subjects are prevented from accessing programs or subroutines that can execute a particular command, for example, to grant read access. Kevin Butler, the security administrator at Nutri Worldwide Inc., wants to set up different accesses to a set of folders on a network. The access should be such that some of his colleagues will have read and write access, while others are allowed read-only access to the files in the folder. Kevin starts the process of selecting a security model. Which security model should Kevin Butler implement in the given scenario? The one-to-one relationship among subjects and objects is the focus of matrix-based model. Kevin should choose the matrix-based model. Let us move on to our next topic, that is evaluation criteria, which are established for the purpose of objectively evaluating the security of a system. In this topic, we will describe evaluation criteria and its uses, list the types of evaluation criteria, and discuss certification and accreditation. We will also look at SEI, CMMI in this topic as well. In this screen, we will talk about evaluation criteria and its uses. Evaluation methods and criteria are designed to gauge the real-world security of systems and products. The following are the uses of evaluation criteria. Evaluation methods and criteria are designed to measure the real-world security of products and systems. It provides a common mechanism to evaluate vendor products by certified third-party evaluation labs. The products are tested against the set of security requirements, and the findings, rating, are published. The primary use of evaluation criteria is it gives a level of security assurance attached to the product. Customers can select products based on the evaluation rating. Let us look into the various types of evaluation criteria. The following are the various types of evaluation criteria. Trusted Computer System Evaluation Criteria, or TCSEC, also called the Orange Book, is the oldest of the evaluation models developed by the U.S. Department of Defense in the 1980s. Information Technology Security Evaluation Criteria, or ITSEC, is European standard for security evaluations. ITSEC addresses confidentiality, integrity, and availability, whereas TCSEC evaluates only confidentiality. The International Common Criteria represent an internationally agreed-upon standard for describing and testing the security of IT products. The Payment Card Industry Data Security Standard, PCI DSS, was created by the Payment Card Industry Security Standards Council, PCI SSC. We will be looking into each of these criteria in the subsequent slides. The Trusted Computer System Evaluation Criteria, or TCSEC, sets the basic standard for the implementation of security protections in computing systems. It was strongly focused on enforcing confidentiality with no focus on other aspects of security, such as integrity or availability. TCSEC was used to evaluate, classify, and select computer systems being considered for the processing, storage, and retrieval of sensitive or classified information on military and government systems. To assist with the evaluation of secure products, TCSEC introduced the idea of Trusted Computing Base, TCB, into product evaluation. The TCB comprises all the protection mechanisms within a system, software, hardware, and firmware. All of these mechanisms need to work in an orchestrated way to enforce all of the requirements of a security policy. When evaluated, these mechanisms are tested, their designs are inspected, and their supporting documentation is reviewed and evaluated. Each of the TCSEC levels describes a different set of fundamental functions that must be in place to be certified to that level. The assurance ratings defined are used to rate products. The main ratings are displayed on the screen. Importantly, it is the move from DAC to MAC between the C level and B levels. Most commercial general-purpose computing systems were never intended for MAC and could only achieve a C2 rating. The more rigid requirements for the higher B and A levels also had the effect of limiting the size and scope of the systems being evaluated and made it highly impractical for them to be used in the development of highly complex, distributed systems. The Trusted Network Interpretation, TNI, brings TCSEC concepts into the network systems. It is often called the Red Book due to the color of its cover. Note that TCSEC, Orange Book, does not address network issues. In the next screen, we will discuss the Information Technology Security Evaluation criteria. Information Technology Security Evaluation criteria, or ITSEC, addresses confidentiality, integrity, and availability, whereas TCSEC evaluates only confidentiality. Security requirements are not prescribed in ITSEC. The consumer or the vendor has the ability to define a set of requirements from a menu of possible requirements into a security target, or ST, and vendors develop products, the target of evaluation, or TOE, and have them evaluated against the target. It provides two sets of levels. They are functional levels and assurance levels, which are evaluated separately by ITSEC. Functionality implies whether the system does what it says, and assurance implies the confidence the organization has in their security methods and the capability to perform consistently, tested by examining development practices, documentation, configuration management, and testing. Let us discuss the common criteria for information technology security evaluation in the next screen. One of the most important evaluation criteria is Common Criteria, CC, for Information Technology Security Evaluation. It is the official name for the international standard ISO/IEC 15408. The international common criteria represent an international set of specifications and guidelines developed for evaluation of information security products, especially to ensure that the agreed-upon security standard for government deployments are met. The thorough evaluation of computer security products is assured by rigorous evaluation of process of implementation, specification, and testing of computer security products. This standard is designed to avoid requirements beyond the current state of the art. It presents a hierarchy of requirements for a range of classifications and systems. The common criteria are the result of the second major international information security criteria effort following ITSEC. They use ITSEC terms such as target of evaluation and security target. CC supersedes TCSEC and ITSEC. Let us look into the evaluation process of common criteria. The common criteria use the following specific terms when defining specific portions of the testing process. Protection Profile, PP. It is an independent set of security requirements and objectives for a specific category of products or systems, such as firewalls and intrusion detection systems. Target of Evaluation, TOE. It is the system or product which is being evaluated. Security Target, ST. It is the documentation describing the target of evaluation, TOE, including security requirements and operational environment. Evaluation Assurance Level, EAL. It is the evaluation score of the tested product or system. In the next slide, we will discuss the common criteria levels. Target of Evaluation, or TOE, is evaluated against one of 7 Evaluation Assurance Levels, EALs. The EAL level is intended to provide the consumer or the vendor with some idea of how confident they should be in the result of the evaluation based on how much information was available to the evaluation lab and how carefully was the system examined. The EALs are as follows. EAL-1, Functionally Tested. EAL-2, Structurally Tested. EAL-3, Methodically Tested and Checked. EAL-4, Methodically Designed, Tested, and Reviewed. EAL-5, Semi-formally Designed and Tested. EAL-6, Semi-formally Verified, Designed, and Tested. EAL-7, formally verified, designed, and tested. EALs are frequently misunderstood to provide a simple means to compare security products with similar levels. Even if assigned the same EAL, products may be different since the functionality may have little in common. We have covered 3 types of evaluation criteria so far. Let us now discuss the last type, that is, the Payment Card Industry Data Security Standard. The Payment Card Industry Data Security Standard, or PCI DSS, was created by the Payment Card Industry Security Standards Council, or PCI SSC. PCI SSC is made up of American Express, Discover, Mastercard, Visa, and others. It is intended to help organizations proactively protect customer account data. It seeks to protect credit cards by requiring vendors using them to take specific security precautions. PCI DSS includes requirements for security management, policies, procedures, network architecture, software design, and other critical protective measures. With this, we have covered all the 4 types of evaluation criteria. Let us now move on to the certification and accreditation process to evaluate the system. Certification and accreditation, or CNA, is the process used to evaluate and approve a system for use. These activities are usually found in government and military environments and in highly regulated industries such as pharmaceuticals and aeronautics. Certification and accreditation is a 2-step process. Certification. It is the process of evaluation of a system's architecture, design, and controls according to the established evaluation criteria. Accreditation. It is the formal management decision to approve the use of a certified system. The following are the standards for certification and accreditation. FISMA stands for Federal Information Security Management Act of 2002. It is a law that requires all United States federal information systems to conform to security standards and processes used to evaluate them. DITSCAP stands for Department of Defense Information Technology Security Certification and Accreditation Process. It is the process used to certify and accredit information systems used by the United States military. DIACAP stands for the Department of Defense Information Assurance Certification and Accreditation Process. It is the successor to the Department of Defense Information Technology Security Certification and Accreditation Process and is used to certify and accredit military information systems. NIACAP stands for National Information Assurance Certification and Accreditation Process. It is the process used to certify and accredit systems that handle U.S. national security information. DCID 6x3 stands for Director of Central Intelligence Directive 6x3. It is the process for protecting sensitive compartmented information within information systems at the United States Central Intelligence Agency, or CIA. This directive defines security standards, classification levels, and the CNA process for certifying and accrediting information systems. The product release reports for the last year indicated a lag in product releases in comparison to the product releases done by Nutri Worldwide's competitors in the respective categories. The management felt the need to use SEI CMMI process improvement model to improve engineering and project management processes. Hilda Jacobs, IT manager at Nutri Worldwide, led this initiative, and Kevin volunteered to be a part of this so that he could apply what he had learned about SEI CMMI process real time. Kevin worked with the team that listed the engineering process areas. They were requirements development, product integration, technical solution, requirements management, verification, and validation. They also selected project planning, control, and monitoring. Hilda identified the processes from the list of processes which require continuous improvement and important to the organization's business objectives. How many levels of process improvement would have been followed by the team led by Hilda? There are 5 levels defined by SEI CMMI for process improvement. Let us move to the next topic, Enterprise Security Architecture. This topic describes how to ensure business strategy and IT security are aligned. In this topic, we will define Enterprise Security Architecture, ESA, and list the common security services in ESA. We will also discuss the Sherwood Applied Business Security Architecture Framework and SABSA matrix. Enterprise Security Architecture, or ESA, implements the building blocks of information security infrastructure across the entire organization. The primary purpose of creating enterprise security architecture is to ensure that business strategy and IT security are aligned. It focuses on a strategic design for a set of security services that can be leveraged by multiple applications, systems, or business processes. Goals and objectives of enterprise security architecture are: long-term view of control. A good architecture must be comprehensive and simple to ensure the organization gets the right level of control to address the most common risks. It must also avoid unnecessary duplication of services or complexities that could compromise the business benefits of the security services. It must be able to address control requirements as they evolve over time. Unified vision for common security controls. By providing this common services model, the architecture looks at security controls from a holistic view, identifying potential gaps in those controls and providing a long-term plan for improvement. Existing technology investment. By focusing on what the organization has already deployed, the architecture can take full advantage of the internal skill sets and minimize the need for training or staff augmentation. Flexible approach. The implementation of the architecture should be flexible enough to provide safeguards and countermeasures for current and emerging threats. Let us look at some common security services in ESA in the next screen. There are a number of security functions that are suitable as foundations for common security services in the enterprise. The following is a sample classification of common security services that may be used as building blocks in Enterprise Security Architecture, or ESA. Boundary control services. These services are concerned with whether information is allowed to flow from one set of systems to another or from one state to another. Access control services. These services focus on the identification, authentication, and authorization of subject entities, whether human or machine, as they are deployed and employed to access the organization's assets. Integrity services. Integrity services focus on the maintenance of high-integrity systems and data through automated checking to detect and correct corruption. Cryptographic services. Cryptographic services focus on common services that can be deployed and reused by a variety of systems like public key infrastructure, or PKI. Audit and monitoring services. These services will focus on the secure collection, storage, and analysis of audited events through centralized logging, as well as the events themselves through intrusion detection systems and similar services. In the next screen, we will look at Sherwood Applied Business Security Architecture Framework, or SABSA. Sherwood Applied Business Security Architecture Framework, or SABSA, is intended to follow the same basic outline provided by Zachman. SABSA is a model and methodology for developing risk-driven enterprise information security architectures and for delivering security infrastructure solutions that support critical business initiatives. The primary characteristic of the SABSA model is that everything must be derived from an analysis of the business requirements for security. The process analyzes the business requirements at the outset and creates a chain of traceability through the strategy and concept, design, implementation, and ongoing manage and measure phases of the lifecycle to ensure that the business mandate is preserved. Framework tools are created from practical experience to support the whole methodology. We will continue our discussion on SABSA framework in the next screen. The model is layered, with the top layer being the business requirements definition stage. At each lower layer, a new level of abstraction and detail is developed. From top to bottom, the layers define the conceptual architecture, logical architecture, physical architecture, the selection of technologies and products, component architecture, and finally, at the lowest layer, service management architecture. The SABSA model is generic and can be the starting point for any organization. However, by going through the process of analysis and decision-making implied by its structure, it becomes specific to the enterprise and is highly customized to a unique business model. It becomes, in reality, the enterprise security architecture, and it is central to the success of a strategic program of information security management within the organization. The SABSA matrix. The primary characteristic of the SABSA model is that everything must be derived from an analysis of the business requirements for security and risk management, especially those in which security has an enabling function through which new business opportunities can be developed and exploited. The risk management focus of SABSA embraces both the notion of opportunity and threat and the balance that must exist between these two concepts. The model is layered, with the top layer being the business requirements definition stage. At each lower layer, a new level of abstraction is developed. From top to bottom, the layers define the conceptual architecture, logical architecture, physical architecture, the selection of technologies and products, component architecture, and finally, at the lowest layer, service management architecture. In other words, the shopping list, in the building trade known as the bill of materials. In addition, the whole area of security service management, administration, and operations is addressed through the operational or service management architecture. In the figure, each of the 6 horizontal layers of abstraction of the architecture model, contextual, conceptual, logical, physical, component, and service management, has been depicted. Each of the sections has a series of vertical cuts through each of the horizontal layers, answering the questions. What are you trying to do at this layer? The assets to be protected by your security architecture. Why are you doing it? The motivation for wanting to apply security expressed in the terms of risk. How are you trying to do it? The processes and functions needed to achieve security. Who is involved? The people and organizational aspects of security. Where are you doing it? The locations where you apply your security. When are you doing it? The time-related aspects of security. These 6 vertical architectural elements are now summarized for all 6 horizontal layers. This gives a 6x6 matrix of cells, which represents the whole model for the enterprise security architecture. It is called the SABSA matrix. See chart. If you can address the issues raised by each of these cells, then you will have covered the entire range of questions to be answered, and you can have a high level of confidence that your security architecture will be complete. The SABSA process of developing enterprise security architecture is a process of populating all these 36 cells. The SABSA matrix also provides two-way traceability. Completeness. Has every business requirement been met? The layers and matrix allow you to trace every requirement through to the components that provide a solution. Business justification. Is every component of the architecture needed? When someone questions, why are we doing it this way? The rationale is plain by tracing the business requirements that drive the specific solution. Hilda Jacobs, General Manager IT Security, is developing enterprise security architecture for Nutri Worldwide Inc. The organization has offices located across many countries. They wanted to implement a uniform security control system throughout the enterprise with a business mandate to be preserved by a chain of traceability. Hilda is looking for reference architecture to begin her work. Kevin had been a great contributor in her last project. She assigned this task to Kevin. Which enterprise security architecture, ESA framework, should Kevin suggest in this scenario? SABSA framework will help develop ESA for Nutri Worldwide Inc. We will start the next topic, System Security Architecture, which is designing security services within individual computing systems. In this topic, we will define system security architecture, list the types of computing platforms, and also identify the system components. System security architecture is focused on designing security services within individual computing systems. Security components can consume considerable resources. Control is frequently sacrificed in favor of improved functionality, usability, or performance. There is a wide variety of computing platforms available, and each platform will take a different approach to providing security services. The architecture of these platforms is fundamental to the ways that they approach security requirements. Most computing platforms will offer a wide variety of security controls to help protect sensitive assets being generated, transmitted, or stored by the system. The CISSP candidate should understand the basic building blocks that make up modern computing systems, as well as some characteristics that distinguish types of systems from each other. Most importantly, they should be aware of the different ways security can be implemented at the system level and be able to choose which mechanisms would be most appropriate in a given scenario. We will move on to the next topic, distributed systems, which is a software system. In this topic, we will define distributed system and list the various types of distributed systems. Let us start with the definition of distributed systems in the next screen. Distributed systems can be defined as a software system in which components distributed on network computers pass messages to communicate and coordinate their actions. Servers, personal computers, workstations, etc. can be part of a distributed system. The goal is to make distributed network components work as a single computer. In the next screen, we will look at the different types of distributed systems. Hilda Jacobs, General Manager IT Security, is under the pressure of bringing the IT infrastructure cost under control due to the increased cost of operations and reduced budgets. She takes a decision that networking components, storage, hardware, and servers that are used to support operations will be outsourced. Hilda Jacobs requests quotations from various vendors to provide the services required by Nutri Worldwide Inc. She assigned the task of selecting the best service model that would suit this requirement to Kevin. This is a great opportunity for Kevin to apply his understanding of the different service models. Which service model should Kevin select based on the requirements of Nutri Worldwide Inc.? Platform as a service would be the model Kevin should choose. This service model provides the networks, servers, storage, and other services that are required to host the consumer's application. The last topic of this lesson is security threats and countermeasures, which describes the security architecture and design vulnerabilities and countermeasures to reduce the associated risks. In this topic, we will discuss the system vulnerabilities and threats and also list the best practices. Let us start with system vulnerabilities and threats in the next screen. Let us first discuss covert channels. Covert channel. It is an authorized, hidden channel of communications that exists within a legitimate communications channel. It can be difficult to detect a covert channel. There are two types of covert channels. A covert storage channel involves a storage location used by a target system. The location may be a memory location, a disk sector, or a file. The unauthorized third party may be able to directly or indirectly read the storage location and gain some level of knowledge about the information stored there. A covert timing channel uses observable timing seen in an information system to determine what is happening in the system. Backdoors. A backdoor is a shortcut in a system which allows a user to bypass security checks, such as username password authentication, to log in. Attackers will often install a backdoor after compromising a system. Maintenance hookups are a type of backdoor. They are shortcuts installed by system designers and programmers to allow developers to bypass normal system checks during development, e.g., requiring users to authenticate. Maintenance hooks become a security issue if they are left in production systems. TOC/TTOU race conditions. A time of check to time of use, or TOC/TTOU bug, is a defect in software or hardware that can result in a malfunction or security violation in a system. Also known as a race condition, a TOC/TTOU bug is one where changes in a system occur between the checking of a condition and the use that results from the check. Here's an example. Two users wish to open a file for exclusive use. The program that each user is running first checks to see if the file is in use. The program for each user reports that the file is not opened by anyone. Due to that, both users' programs open the file, expecting that they each have exclusive use of the file. Malicious code, malware. Malicious code, or malware, is the generic term for any type of software that attacks an application or system. There are many types of malicious code that can cause damage to targeted systems, among them viruses, worms, Trojans, and logic bombs. Zero-day exploits are malicious code, a threat for which there is no vendor-supplied patch, meaning that there is an unpatched vulnerability. Computer viruses, worms, and Trojans. Computer viruses are malware that does not spread automatically. They require a carrier, usually human, and are frequently spread via floppy disk and, more recently, portable USB, universal serial bus memory. Types of viruses include macro, a virus written in macro language, e.g. Microsoft Office or Microsoft Excel macros. Boot sector, a virus that infects the boot sector of a PC, which ensures that the virus loads upon system startup. Stealth, a virus that hides itself from the OS and other protective software, such as antivirus software. Polymorphic, a virus that changes its signature upon infection of a new system, attempting to evade signature-based antivirus software. Multipart, a virus that spreads via multiple sectors. Worms are malware that self-propagates, i.e. spreads independently. A Trojan, also called a Trojan horse, is malware that performs two functions, one benign, such as a game, and one malicious. Rootkits. A rootkit is a malware that replaces portions of the kernel and/or operating system. A user mode rootkit operates in Ring 3 on most systems, replacing operating system components in user land. A kernel mode rootkit replaces the kernel or loads malicious loadable kernel modules. Kernel mode rootkits operate in Ring 0 on most operating systems. Logic bombs. A logic bomb is a malicious program that is triggered when a logical condition is met, such as after a number of transactions have been processed or on a specific date, a time bomb in this case. Malware such as worms often contain logic bombs, behaving in one manner and then changing tactics on a specific date and at a specific time. XML. Extensible Markup Language, XML, is designed as a standard way to encode documents and data. It is similar to HTML and is used on the web, however, not tied to it. XML can be used to store application configuration, to output from auditing tools, and for many other tasks. Extensible means the users may use XML to define their own data formats. Security Assertion Markup Language, SAML, is an XML-based framework for exchanging security information, including authentication of data. Some forms of single sign-on, SSO, use SAML to exchange data. Applets. Applets are small pieces of mobile code that are embedded in other software such as web browsers. Unlike HTML, hypertext markup language, which provides a way to display content, applets are executable. Applets can be written in a variety of programming languages. Two prominent applet languages are Java by Oracle Sun Microsystems and ActiveX by Microsoft. The term applet is used for Java, Control for ActiveX, however, they are functionally similar. In this screen, we will discuss the best practices which can be used to control the system vulnerabilities and threats. The best practices are process isolation, data hiding, abstraction, cryptographic protections. Process isolation is a logical control that attempts to prevent one process from interfering with another. This is a common feature among multi-user operating systems such as Linux, Unix, or recent Microsoft Windows systems. Data hiding maintains activities at different security levels to separate these levels from each other. This assists in preventing data at one security level from being seen by processes operating at other security levels. Abstraction hides unnecessary detail from the user. The computer is a complex machine, and the more complex a process is, the less secure it is. Abstraction provides a way to manage complexity. Cryptographic protections can be used in a variety of ways to protect sensitive system functions and data. By encrypting sensitive information and limiting the availability of key material, data can be hidden from less privileged parts of the system. Let us summarize the topics covered in this domain. An architecture framework provides a structure used for developing a broad range of security designs. Security models are the rules to be implemented to support and enforce security policy. The various types of evaluation criteria are Trusted Computer System Evaluation Criteria, Information Technology Security Evaluation Criteria, Common Criteria, and Payment Card Industry Data Security Standard. Enterprise security architecture implements the building blocks of information security infrastructure across the entire organization. System security architecture is focused on designing security services within individual computing systems. The various types of distributed systems are virtualization, hypervisor, cloud computing, grid computing, and peer-to-peer. The best practices which can be used to control system vulnerabilities and threats are process isolation, data hiding, abstraction, and cryptographic protections. In the next domain, we will learn about physical security in detail.